Some people may already know the logarithm function in the real numbers. It's the inverse function of the exponential function e to the power of x and defined for every positive number x. You will find a logarithm button on most scientific calculators. There are also some calculation rules. E to the power of log x and the logarithm of the exponential function result in x again. The reason for this is that these two functions are inverse to each other. Especially these two rules are pretty nice. The logarithm of x1 times x2 is the logarithm of x1 plus the logarithm of x2, and the logarithm of x to the power of r is equal to r times the logarithm of x. This means we can change a multiplication to a summation, which you can see here, by using the logarithm and put exponents in front of the logarithm, which you can see here. For example, you could write the logarithm of 6 as the logarithm of 2 times 3, and by using this first rule here, you can write the logarithm of 2 times 3 as the logarithm of 2 plus the logarithm of 3. Or you could write the logarithm of 2 to the power of 42 by using the second rule here as 42 times the logarithm of 2. So these calculation rules work really nice for the real logarithm. Maybe you have also heard something of complex numbers. They look like this here. So z is a complex number and it is written like that: x plus I times y. X and y are both real numbers. X is called the real part of the complex number z, and y is called the imaginary part of the complex number z. You can write it like this here. So x is the real part of z and y is the imaginary part of z, and as I said before, both of these numbers are real numbers. I is called the imaginary unit and it fulfills that I squared is equal to -1. You can visualize complex numbers in the complex plane like this here. So here you have the real part x, here you have the imaginary part y, and this here is the complex number z visualized in the complex plane. You can also write down complex numbers by using polar coordinates. To do so, you need this angle here and the absolute value of the complex number, which is the length of this vector here. So the length of this vector is also called absolute value of z and can be calculated like this here. And the angle, this angle here, is also called the argument of z. This angle phi can be calculated, for example, by using trigonometric functions. Now you can write down z in polar coordinates, which looks like this here. Z is equal to the absolute value of z times e to the power of I times the argument of z, which is this angle phi here. This representation is not unique, because we can always add 2 pi to the angle phi and get to the same complex number again. So to make this representation unique, we have to say that the angle phi or the argument of z has to be, for example, between -pi and pi. Because complex numbers are pretty important, people also defined the logarithm for complex numbers. So the complex logarithm is defined as follows. So the complex logarithm of a complex number z is defined as the real logarithm of the absolute value of z, which is a real number, so the absolute value of z is a real number, plus I times the argument of z. And we want this angle, or the argument of z, to be in this interval here. So between minus pi and pi again. This is very important. So this condition here is important. Let's do some calculations now. So we can write 0 as the complex logarithm of 1. This is the same as for the real logarithm. Now we write 1 as minus 1 times minus 1 and get this here. So the complex logarithm of 1 is equal to the complex logarithm of minus 1 times minus 1. At this point here, we use our rule to change a multiplication into a summation. So the complex logarithm of minus 1 times minus 1 should be the complex logarithm of minus 1 plus the complex logarithm of minus 1. So this here is 2 times the complex logarithm of minus 1, and this is equal to this here. So we have to calculate the complex logarithm of minus 1 now. To do that, we need the argument of minus 1, so this angle here. So the argument of minus 1 is just pi. And we also need, so we need the argument of minus 1, and we also need the absolute value of minus 1, which is just 1. Then we can insert here and get the following for the complex logarithm of minus 1. So this is 2 times the real logarithm of 1 plus I times the argument of minus 1, which is pi. Because the real logarithm of 1 is 0, this here results in 2 pi times I. But now we can multiply this complex number here at both sides and get to 0 is equal 1. So our calculations with the complex logarithm resulted in 0 is equal 1. If you have already watched my video about the trivial ring, the one with the title "We Can All Be a President", then you know what that means. It means nothing good at all. So, have we ruined mathematics now? Does this mean the death of mathematics? No, it doesn't. No worries, you have to lay all your trust in the force, I mean mathematics now. Every time my calculations resulted in something that just seemed wrong, I found out after a while that I did something in the calculation that was wrong or not allowed. In our example, this is the case too. The mistake can be found here. When working with the complex logarithm, it is not always allowed to change a multiplication in a summation. So the calculation rule that the complex logarithm of z1 times z2 is equal to the complex logarithm of z1 plus the complex logarithm of z2 is not true at all times. So it is not true for all complex numbers z1 and z2. It is only true if the angle of z1 or the argument of z1 plus the argument of z2 lies in this interval here again. So if the argument of z1 plus the argument of z2 is between minus pi and pi again. Only if this is the case here, so if this condition here is the case, you can use this calculation rule here. Okay, once again, this calculation here is okay. So you could write the complex logarithm of minus 1 as the complex logarithm of I times I, because I times I is I squared, and this is equal to -1. And then you can use this rule here and write it as the logarithm of I plus the logarithm of I, which is 2 times the logarithm of I. And to calculate the logarithm of I, you can take a look here. So you need the argument of I, which is pi half, and you need the absolute value of I, which is 1. And then you just insert in the formula for the logarithm and get pi half times I, and this is 2 times the logarithm of I, so in the end you have I times pi. But the important thing here is why we can use this rule here. I already told you can only use this rule under this condition here. So we have to check if this condition holds true in this example here. So this here only works because the argument of I plus the argument of I is equal to, so the argument of I, you can see it here, it's pi half. So argument of I plus argument of I is pi half plus pi half, and this is equal to pi. And pi is inside of this interval here. So this condition here holds true. So we can use this calculation rule at this point here. This calculation here is not okay. So for example, you could write the logarithm of 1 as the logarithm of -1 times -1. And you now try to write this logarithm as the complex logarithm of -1 plus the complex logarithm of -1. Here it is not allowed to use the calculation rule. Why? Well, we have to check if this condition here holds true. If it holds true, we can use the calculation rule. If it doesn't hold true, we are not allowed to use it. So we are not allowed to use this calculation rule at this point here because the argument of -1 plus the argument of -1 is equal to. So we have to find the argument of -1. You can see it here at this point. So the argument of -1 is just pi because it's this angle here. So the argument of -1 plus the argument of -1 is equal to pi plus pi, which is equal to 2 times pi, and 2 times pi is not inside of this interval anymore. So we are not allowed to use this calculation rule at this point here. So be careful when using the complex logarithm, because it can lead to strange and wrong results pretty fast. By the way, you can also define complex exponential functions the following way. Z to the power of r is equal to e to the power of r times the complex logarithm of z. And in this case, z and r can be some complex numbers. When doing this, the following calculation rule is not true all the time when also considering complex numbers. So we are talking about the following rule, that the complex logarithm of z to the power of r is equal to r times the complex logarithm of z. When considering the real logarithm, this rule is always true, but when considering complex numbers, this rule is not always true. It can only be used if this extra condition here holds true. So this calculation rule is true when the imaginary part of r times the complex logarithm of z is in this interval here, so between -pi and pi. If this here holds true for some complex numbers r and z, we can use this calculation rule here. If you ignore this extra condition here, you will get wrong results. Just look at this example here. So this calculation would be not okay. So you could write 0 as the logarithm of 1. This is equal to the logarithm of e to the power of 2 pi I. Now we try to bring this exponent here, 2 pi I, in front of the logarithm. So we get 2 pi I times the logarithm of e. The logarithm of e is 1. So this is equal to 2 pi I. And in the end we get 0 is equal 1 again. So here we are again. I am the president again. We are not allowed to bring the exponent in front of the logarithm at this point here, because of this condition here. So we have to check if this condition holds true. When it holds true, we are allowed to use the rule. If it doesn't hold true, we are not allowed. So we have to check if the imaginary part of r times the logarithm of z, so if the imaginary part of r, this is r, 2 pi I, times the logarithm of z, which is e in this case, is inside of this interval here. So the imaginary part of 2 pi I times the logarithm of e is just 2 pi, and this is not in this interval here. So we are not allowed to use this calculation rule at this point here. So be careful when working with the complex logarithm. Otherwise, you will get really weird and wrong results.